senior student majoring in computer science at BITS Pilani, India. I joined the group around a couple of months ago, so I've been on and off, but my sort of resolution, at least for this new year, is to be more active in the group and I just participate in the conversations more. So I decided to volunteer as one of the presenters for the Spring 2024 sessions. So yeah, this is my first time presenting, and I'm still an undergrad, so yeah, the presentation might not be as detailed or as precise maybe as you might be used to, but yeah, I'm just taking this as an opportunity to present whatever I understand and just get feedback and like constructive discussion from the group. So yeah, the paper I'll be presenting today is called Chablis, Fast and General Transactions in Geo-Distributed Systems. So yeah, first, some quick background on what's the problem and why we're doing all this, right? So this is property called external consistency, or what we know more commonly, I'd say, as strict serialization. It's like the holy grail or like gold standard in database isolation and consistency semantics in general. So it basically consists of two properties, which is one is serializability. So given like an execution, like the entire execution or like even a slice, just execution consisting of a set of transactions, there should be a serial ordering for the transactions. So there should be like a strict ordering within each transaction and in a linearizability, right? So if transaction A has committed before transaction B in the execution sequence, then in the serializable representation, A should be ordered before B, right? So just a quick example here of what is strictly serializable and what is not. So in the second sort of column, you can see in P1, we're writing X to B as well as we're writing Y to B, right? So in the end, you can interchange either of them, and there'll not be a strict sequence of what to do, right? Because we're writing both X and Y at the same time to B. So this does not give rise to a proper ordering, you can say. But here, since we don't have any read-write conflicts and we're just reading this section, we're writing X to A in P2, and we're basically writing X to B and Y to B as well, right? So in this sense, you can say that we have strict serialization in that sense. So, I mean, it's basically the fact that you have for all interpretations, you can say of the transactions included in the execution, you have one set order for the transactions included in the execution. So within to achieve this property, right, we have two trade-offs that modern geo-distributed systems make, which is either between speed or between generality. So if the systems make a trade-off with speed, so for example, they offer a general programming model, so you can say like normal SQL, and you can do almost whatever you want with the database, but and you can express it in the expressibility is pretty good as well. But what happens here is you make sacrifices in latency in one way or another. So, for example, if it's in geo-distributed systems, there's multiple regions, so the latency factors can include, I mean, many cases, but like the common ones are, say, cross-region round trips for every write transaction that you do. And for something like, say, Google Spanner, you have like a wait period that you have to cross the clock uncertainty, which induces like a delay within the writer. So yeah, so in general systems, the trade-off you have to make is between speed. The other end of the spectrum is where you make a trade-off with generality. So you can have fast, low latency, and high throughput cross-region writes, but to achieve that, you need some specific properties, say, for example, deterministic execution, which leads, I mean, downstream to a restricted programming model. So you can't have the expressivity that you can say with something like Spanner or something which is like more sort of generally supported, and hence you have to make some like the programmers have to make trade-offs and have to learn like the integrities and the specifics that these systems require, which again leads to loss of generality. So we come to the question: is this trade-off necessary? I mean, can you be fast and general as well? So the answer is yes, and the paper which highlights that is called Chardonnay. I believe it has been discussed. But yeah, a quick refresher on Chardonnay is that the main idea is that 2PC isn't the bottleneck in distributed transactions. It's the slow I/O, so writing to the SSD, or maybe latency networking. All of these can and are factors of like the majority contributing factors or bottlenecks in the latency calculation, right? So we can speed up this 2PC using low latency networking and storage. So what this means is we can achieve fast and general transactions, but I mean, at least in Chardonnay, we do that in a single data center or a single region, is what is called in the context of geo-distributions. There's no fancy stuff to be done, so transactions execute, they run using two-phase lock and two-phase commit. So yeah, the architecture is also pretty simple, I'd say. So you have three components within Chardonnay. So one is the local epoch service, which is actually a very simple component. It's just one number, which is within a replicated state machine. All of these state machines come to consensus using multi-pack source. And it's just a single number, which is incremented at a regular pace. So it's incremented monotonically without any dependence on transactions. So it's like a pseudo clock, you can say, of some manner. So for example, you can have an epoch that runs monotonically every 5 seconds. The second is a key value service, which stores the user's key value data. So the entire key space or the key universe is divided into these ranges, right? And each of these ranges has for any given time interval or an epoch interval. And the third is the transaction store. Again, it is like a replicated store for committed transactions, so that client failures don't end up blocking transactions. The main thing to note here is that transactions in Chardonnay read the epoch value after execution. So it's not like it's being written to, there's anything else done with it. It's just being implemented every I mean, at just set time interval as a certain system. But transactions read the epoch value after each execution. They do so via an RPC call called read underscore epoch. And the most important point to note here is that if read underscore epoch returns C, all subsequent calls, like from any client to read underscore epoch should return a value which is greater than or equal to E. So this is like a transaction lifetime in Chardonnay. So you have a client. What it first does is it starts a transaction in the transaction state store. After that, it executes the transaction by interacting with the key value service. After that is the 2PC stage. So you send a prepare transaction, you get a prepare transaction back from the key value service. After that, 3B involves reading of the epoch, right? So you read the epoch number, and you basically, after reading the epoch number, you basically get a prepared message back from the key value service. After that, you log the commit, which includes the epoch value. And after that, you commit the transaction and release all the locks so that transaction execution is finally done. So we get what is known as a leader disjointedness problem in Chardonnay. So the problem is that within the key universe, if you remember, there's multiple ranges which have leaders as well, right? But leader obviously then leads to the fact that there are many replicas for each range, right? So the problem here is that there's the potential for multiple replicas to believe they are the leader at the same time. So we don't want that inconsistency, otherwise it will lead to like correctness issues and just overall inconsistency in the system. So an example of this is, say, a range is replicas R1 and R2. R1 is the initial leader, and its lease epoch, which is, the time interval for which it is the leader is 1 to 100. So it is a leader for 1 to 100 epochs. After that, say R1 crashes in the middle of this, R2 takes over, and it has a lease epoch of 50 to 150. After that, R1 recovers at some point of time, say it's 60 or 70. Both R1 and R2 think they are the leaders for epoch 50 to 100. So what do you do in this scenario? So the solution is simple. So each range replica maintains a lease with an epoch interval. So a lease acquisition, which is basically uh, leaders saying that, hey, I want to be a leader for this amount of time, is done by appending an entry into the Paxos log, which is maintained, like distributively maintained among the leaders, among the replicas, right? So the lease entry includes the replica ID and the epoch interval at which they're going to lease, to acquire the lease for. Replica attempting to acquire the lease appends an entry to the Paxos log. Again, it includes replica ID, epoch interval, in the most recent lease that it is aware of. Now, what happens here is that the replicas check what the most recent lease is, and they reject the attempt if they are aware of more recent lease. So, for example, in example that we discussed earlier, in this scenario, if there are more replicas as there should be, so R3, R4, R5, all of them will agree that the latest, the upper interval for the lease epoch of R2 is 150, and hence it is, sort of more delayed, and it is the latest lease epoch. So it'll all of them will prefer R2 to be the leader instead of R1. So yeah, this Paxos logging, this overall mechanism ensures that only one replica can successfully acquire the lease for any given time interval. So this is all fine. So Chardonnay works only for one. Yeah.
So it looks so epoch services, is it then only used to correctly find the leader and not to serialize the transactions?
No, it is used to serialize. Like the main goal of local epoch service is to serialize the transaction. Since uh, I, I think I didn't cover it in a lot of detail, but here I mentioned that the main idea here is that transactions read the epoch after each execution. So we have strict serializability in the sense that if a transaction reads an epoch E and commits, and then another transaction reads the epoch and commits at a later point of time, we know that at a later point of time, say at T2, E2 is greater than E1. So we have order that T1 occurred before T2. So, the epoch is really important to order the transactions, but again, you have multiple leaders in order to ensure, you have multiple replicas and leader to coordinate to ensure fault tolerance as well, right? So, this leader disjointedness problem arises due to fact that we have multiple replicas and we have leaders for each for a given time interval.
But it also seems that the epoch services advancing the epoch very infrequently, right? Like every 5 milliseconds or so.
Oh no, not infrequently. Actually, very. You can set the interval, but it uh, increments it at a regular interval. So it's like, every 5 seconds, for example.
Gotcha. But then does that not say that you can only have one transaction every interval? Whatever that interval is, second or 5
Not
seconds.
not really, because it's not strict. For example, you have one epoch, right? So if say one transaction commits at say you have a write transaction and you want to commit. You have conflicting write transactions and you want to commit them. For example, let's say um, one transaction is committed E1, the other is committed E2. So yeah, in that sense, you're correct that if you have two conflicting transactions, in order to order them, they need to be at least one epoch away.
Exactly.
That's all. But it's for it's for conflicting rights, right? So for example, if there's no lock on a certain key for that time interval. So if the key set or like the range you're operating on is completely different, you can have multiple transactions, right? But yeah, for say the same key, you acquire the lock for that epoch interval. Once you finish committing, yeah, the other one can commit at the next epoch.
Yeah, that's a good point. That should help with avoiding conflicts too often. Thank you.
Yeah. Yeah. So, how do you generalize Chardonnay for multi-region systems, right? So, Chardonnay works only for a single data center. So, like like off the top of everyone's head, like the options we have are you have a local epoch in each region and you read it. Might be a viable solution, but in the end, you'd have to do consensus reads, right? Since each local epoch has to be the same exact value, there'll be conflicts. So it'd be the same as, say, cross-region latencies that you encounter in, say, something like something like a spanner, not spanner, but other data bases which use cross-region, like which have generality and sacrifice speed. The other option is you have one single epoch and you read. No, again, that would mean that for transactions not within the region where the epoch is located, you'd have to do cross-region writes again, so that lead to cross-region latencies. So the solution here is Chablis, which is like a generalized or an extended version of Chardonnay. So the only additions that Chablis makes to Chardonnay is the two components, which is the global epoch service and an epoch publisher. So a global epoch service serves the same purpose as a local epoch service. It is an ordering service, if you might say. So there's again a number um, which is used to like give strict serializability to transactions. And instead of like the second option that we discussed, instead of being located in just one region and having other regions to cross region rights, it has an epoch publisher. So where it publishes the epoch every time it updates, and the epoch publisher is located in every Chablis region. So the architecture looks something like this. So there's a global epoch service. You have Chardonnay running. Chablis region consists of Chardonnay and an epoch publisher. And once the global epoch updates again, it might be as frequent or as infrequent as the local epoch service, but it is incrementing at a regular pace. So once you have the global epoch service, it publishes the epoch number to epoch publishers, which is then uh, served to the Chardonnay uh, system within the Chablis region. So you have two RPC calls instead of one. So you have read underscore global epoch and read underscore local epoch. So the epoch publisher serves the read underscore global epoch RPC file in each Chablis region. So yeah, we can look at what the transaction lifetime in a Chablis client is. So the first is again you start a transaction. The second one is you interact with the Chardonnay key value service, read sites, whatever. After that, the two-phase commit, which is you send a prepare message. After that, you read the local epoch. Now, just one step is added within this is that you also have to read the global epoch. So it reads the global epoch from the global epoch publisher. And after that, it validates that the LR is essentially the local epoch. It falls within the least epoch interval of each range leader. So each range leader, again, as we discussed, it has a Paxos log of the various epoch intervals, right? So the upper interval, for example, 50,150, as we've seen in R2, and the LR, for example, there is 100. And all of the replicas agree that since it's 50 to 150 and the current epoch number is 100, the leader is R2. You validate this, and after that, after this validation, the transaction aborts if it fails for any range leader. Else, you commit the transaction. stored in the transaction state store. Notify the key value service that you have committed the transaction and release any locks. And if if you're aborting as well, in this case where the replicas don't agree on the lease epoch interval or LR, essentially you notify the key value service anyways to abort the transaction and release any locks. So the other case, right, which is multi-region read-write transactions. Within this also, there are two subcategories, which is you have multi-region reads as well as writes. So this will be like a full generalization of the single read-write transactions where you, and obviously there'll be cross-region latency since you'll have to visit each region, you'd have to calculate and validate the LR within each region. And there's then that induced cross-region latency due to, since it follows just a very similar pattern, but at a global scale as we saw in single region read writes. However, if it's a single region write, but the execution involves multi-region reads as well, transactions can use what is known as snapshot read in isolation. So you have to specify in the transaction itself that it that it is this type of transaction. Otherwise, it will be flagged as this transaction, and you'll end up facing cross-region latency anyway. To sort of avoid that latency, you need to specify that transaction is a single region write and multi-region read. Snapshot read algorithm is something as follows, right? So you have this start transaction procedure. What it does is first reads the global epoch from the global epoch publisher. Now what it does is it waits for the global epoch to advance at least once, so that, I think Sandeep had asked the doubt, so the same thing, right? So as to guarantee that any transaction that might be conflicting and is at the prepare stage at least has an epoch of at least EC, right? So that we don't have any sort of conflicting transactions in at least the global scenario. So after that, it returns EC as a snapshot epoch since the transaction read the epoch at EC and not at EC plus one. The EC plus one is just that safety net or that safety interval that you follow so as to not have conflicts. After that, you read the keys, read key K, EC, LR for each key K. Then you execute on the leader of the range, which contains the key K. So again, the same thing. You have the local epoch LR, which represents the current epoch in the region. If LR is not provided, which usually is not, you read it from the local epoch service. And again, as you do in single read-write transactions, you validate whether LR is correct or not by seeing the leader's lease epoch interval. You ensure that the leader is still valid for the local epoch by seeing whether LR is less than the epoch's upper interval. So for example, if LR is currently 100 and the leader is R2 and R2's lease interval is 50 to 150. Right? So in that case, LR is valid since the upper interval hasn't expired yet. But if like the replicas have, the fact is that the leader's upper interval is say something like 90 and the LR provided is 100 for some reason, then it means that there's some inconsistency in the system and you should abort the transaction. So this is basically the validation step. After that, you wait for any write locks on K to be released, since again, you don't want any conflicting transactions, plus you want strict serializability as well. After that, you read the version of K, which is a snapshot epoch EC, since that's a snapshot that the transaction is committed at. After that, you retrieve a consistent snapshot of the data at epoch EC, and you return the read value. You do this for all regions, right? After that, all reads complete successfully. The transaction finishes. So even if one read aborts, the entire transaction aborts, right? Because we need to be consistent throughout. So if out of all these, any read aborts, we like the transaction fails, the count is an error, and the entire transaction works. So, yeah. So the final case, evaluation and comparison. So the authors have compared it mostly to something like Google Spanner, which has pretty good multi-region read latencies. So the benchmark which is used is YCSB benchmark. P50 essentially means that you do 50% reads and 50% writes. And the scenario here is you do the case that we just described using the snapshot read algorithm, which is single region reads, multi-region writes. However, irrespective of what write Spanner does, it's much slower than Chablis, taking in the order of milliseconds for any sort of writes, while Chablis is in the order of hundreds of microseconds. Yeah, the authors then conclude by saying that it's not really a fair comparison since Spanner does not use fast RPCs or like very optimized networks and storage as Chablis does, but it is expected to be slower in that case too, since we have that inherent clock uncertainty that Spanner has to wait out during the commit phase. So, yeah, thank you.